Bam! Mr. True here. Are you tired of doing derivatives? Well, I got the cure for you. It's called the antiderivative. We're going to undo all those derivatives. You know, do the inverse math operation. We're going to do that through a concept called integration, which we're going to build on. This is just the start of building the concepts to allow you to do integration, which is going to undo that derivative process, allow you to, with indefinite integration, find a version of, or if a little extra information is given to you, find the actual original function that gave you this derivative. Now, we are going to need a little bit of extra information, which we're not going to deal with in this video, to allow us to find the actual original function that gave us this derivative that we're trying to undo. Without that extra information, we're just going to have the ability to find the general antiderivative, which is what this video is about. Part 2 is going to be where we can find the actual original function. To explain what I'm talking about here, I'm using some notation, which I'll change in a second to match the definition that we're going to deal with, but we have, you know, kind of like in this 3 chapters of my book anyway, that we do derivatives in the beginning. We'll just label this f of x and f prime of x, indicating that we found a derivative. So I have 3 functions here. Y equals x to the 4th, x to the 4th plus 2, and x to the 4th minus 5. So 3 different original functions. Now, remembering that the first derivative allows us to find the slope of a curve along, you know, pretty much any given value of x where the function is defined. We'll look at what the plus 2 and the minus 5 is. When you have an addition of a constant at the end of a function, all it is a vertical shift. So if I take a graph that maybe has a slope here of 2, so the first derivative when you plug in this particular value of x would equal negative 2, if I take that function and I just move it up a few places or down, the slope at that value of x is still going to be the same. The graph has just been moved vertically, or, you know, up or down. So the slope at that given value of x is not going to change. So it makes sense to say that, and know that, you know, we have these 3 original functions, but yet the derivative of each of these functions is 4x cubed for all of them. And that's because the derivative of a constant is equal to 0. So whether there's a plus 0, plus 2, or minus 5, all of those are basically going to disappear through finding the derivative, because the derivative of a constant is equal to 0. Thus, you get the same answer 3 times. So to match this definition of antiderivative, and remembering that and realizing that we're going to be given the derivatives and have to go back and find the original function or the antiderivative, we're going to change the notation a little bit and say that we're given the lowercase f. When we're given this derivative for the definition here, when we look at the derivative, we're going to say that that's a lowercase f. And when we go through the indefinite integration process, we're going to be trying to find the original function, which we're going to call capital F of x. The definition of an antiderivative: a function f is an antiderivative. We are not going to be able to find the actual original function. We're not going to be able to find out what that constant was at the end of the function, if there was one, unless we have some more information given. So is an antiderivative of lowercase f on an interval I if the derivative of capital F of x is equal to lowercase f of x for all x and I. So this right here is basically telling you how you can check your work. When you're given something that you're told is a derivative, and you go through the indefinite integration process to find the antiderivative, if you want to make sure that your work is correct, just take the derivative of your answer to see if you're given, or see if you arrive at the original derivative you're given. The antiderivative of f of x equals 4x cubed, this is kind of getting into the formal definition I'm saying in front of. The antiderivative of f of x equals 4x cubed is capital F of x is equal to x to the 4th plus c. Okay, the derivative of that constant is equal to 0. And again, without extra information given to us, we can't find out what that vertical shift or that constant actually is at the end of the function. And this is, with the plus c, called a family of all of the possible antiderivatives. Now we're also going to be learning something called a definite integral, or work through the process of definite integration. That's going to allow us to find the integral within a particular boundary. This is an indefinite, so there is no boundary, and thus we're going to be looking for that original function. But I probably shouldn't have brought that up because we're not going to deal with definite integrals in this video. Representation of antiderivatives. If f is an antiderivative of lowercase f on an interval I, then capital G is an antiderivative of f as well on the interval I, if and only if g is in the form of g of x is equal to f of x plus c. So we're saying that we need to add that plus c at the end of our answer to represent the general antiderivative, or to represent the family of all antiderivatives. Let's get to that next page of notes. Here we have the notation for antiderivatives. dy over dx, the derivative of y with respect to x, is equal to f of x. That lowercase f, again indicating a derivative. Instead of the f prime of x, because I'm using the notation that was in our definition of antiderivatives. We're going to take this dx, or it could be dt, it could be d theta, whatever we found the derivative of with respect to that variable. We're going to take that dx in this case and multiply it to both sides of this little equation for convenience sake, and say that dy is equal to f of x times d of x. And you'll see why that is down here in a second. Now, what we're going to be asking is, what is y? What is the original function if dy equals f of x times dx? In other words, we want to go from the derivative to the original function. That means we want to do an indefinite integration. So that indefinite integration symbol, or the integration symbol here, is this sort of long, stretched out sort of s. Think of it as a sum idea, because when we do definite integration, but we're not there yet. So we're going to have this indefinite integration symbol here of f of x dx. Now f of x is our integrand, and the dx is our variable of integration. You know, sort of like the variable that we found the derivative with respect to is now going to be undone with it as the variable of integration. And then we have the equals capital F of x, that original function, again, plus c, our constant of integration, that constant that we can't find unless we're given a little bit of extra information. The integral of f of x dx is read the antiderivative of f with respect to x, so the antiderivative of f of x with respect to x. The operation of finding all solutions of this equation is called antidifferentiation, or the indefinite integration. I said those words again through the whole video, but I wanted you to basically just see that concrete definition there. Well, here we have a list of our basic differentiation formulas. We have the derivative of a constant equals 0. The derivative of a constant times x is equal just that constant, so the derivative of 2x is equal to 2. We have the derivative of a constant times a function is equal to that constant times the derivative of the constant. We have the derivative of the sum of terms is just the derivative of each individual term, whether it's addition or subtraction separating them, that's fine. And then we get to, I'm going to try and leave all these up here as I do my examples, so I kind of cram these together. So I put a star down here. We have the biggie that we're going to be dealing with, the power rule, which says the derivative with respect to x of x to the n is equal to n times x to the n minus 1. So when we do the derivatives, we reduce that exponent by a value of 1 and take the original exponent and move it down out front. So in other words, the derivative of 3x is 3x squared, at least the derivative with respect to x. Now, integration is just the opposite of the indefinite integration, is just the opposite of doing the derivative. So the indefinite integral of, excuse the interruption there. So we have the integral of 0 with respect to x is equal to c, just the opposite of the derivative of c is equal to 0. We have the integral of k dx is equal to the k times x plus c. Again, just the opposite of finding the derivative. We have the integral of a constant times a function with respect to x is equal to the constant, that same constant, we can pull that out in front of the integral notation, and that's that constant times the integral of that function. We have the integral of two functions being added together is, we can pull that apart and give each term its, or find the integral of each individual term, again with the plus or minus in the middle, doesn't make any difference. But again, the big deal here is the power rule. The integral of x to the n dx is equal to x to the n plus 1. We're taking that exponent and raising it up by 1 as opposed to reducing it by 1 as we did with the derivative process, and then dividing that term by n plus 1. So we're going to raise that exponent by 1 and then divide by that same exponent that we have after we've increased it by a value of 1. And of course this is plus c, that constant at the end. Now we cannot divide by 0, so n cannot equal 1 with this power rule for integration. Now the derivative of sine with respect to x is cosine, so the integral of cosine dx is equal to sine x plus c. The derivative of cosine is equal to negative sine, so the integral of sine, now that negative has kind of gone away, but we've basically just moved it to the other side of the equation, multiply both sides by negative 1 if you will. So the integral of sine x dx is equal to negative cosine x plus c. We have the derivative of tangent with respect to x is secant squared, so the integral of secant squared x dx is equal to tangent x plus c. We have the derivative with respect to x of secant is secant tangent, and so the integral of secant tangent is equal to secant plus c. Cotangent gives us negative cosecant squared with derivative, so the integral of cosecant squared x dx is equal to negative cotangent x plus c. And again, the same thing here with the cosecant function, which gives us negative cosecant times cotangent when we do derivatives. The integral of cosecant x cotangent x dx is equal to negative cosecant x plus c. We're going to refer to all these as we go through our mini examples I'm about to do with you. And please be aware that when you do the integration process, you need to make your problem exactly match what you see here in these formulas. So if we were trying to find the integral of cosine squared, that's not exactly cosine, so that could potentially give us some problems as we're just starting to learn how to use our basic integration formulas. I got a lot of examples, so let's get those started. Oh, excuse me. Yes, let's get those examples going. Here's our first two examples. We want to find the integral of 5x dx. So we're going to use this rule right here that says the integral of x times a function dx is equal to that constant pulled out, and then we're just going to find the times the integral of f of x dx. So we're going to take this constant of 5, pull it out, and write this as 5 times the integral of x dx. And then we're going to use the power rule to find the integral of x. Now this has a power of 1, so we're going to again use this power rule. This is the biggie here. We're going to raise that exponent by 1 and then divide by that increased exponent. So it's going to be 5 times x squared. So we've raised that power of 1 by 1. So now we're going to divide by that 2 plus c. Now we're going to take that 5 that's in front of these parentheses here and distribute it and get 5x squared over 2 plus 5c. Now c is defined as a constant and any constant. So writing 5c is a little bit, it's unnecessary and overcomplicated. We can just simply write that as c. So we can rewrite this as 5x squared over 2 plus, again, this value of c. This idea of taking this constant and pulling it out front, finding the integral, and then multiplying it back in is always going to sort of create this basically overcomplicated version of the constant. So we're going to streamline that process in this next example and show you that that's not really necessary to show that you pull it out of the function before you find the integral. And what the 4 steps we're going to do with all of these problems is we're going to look at the original problem. We're going to rewrite it to get it to match one of these integration formulas, these basic integration formulas exactly. We're going to apply that integration or integrate and then simplify the expression or whatever is left. So when we see negative 8 over x cubed, this is a quotient here, right? we don't have a quotient property over here. We don't have a product property either. We only have the power rule. So I need to get this into some kind of format that allows me to use that, that power rule. And we're going to do that by, writing this so that we don't see that fraction bar, so that we don't see the quotient. So we're going to write this as the integral of -8 x to the -3rd power dx. And see, so now my division sign is gone. I don't look at it as a quotient. It's just a term that I can apply the power rule to. So again, we're going to take this exponent. We're going to increase it by 1. And -3 plus 1 is -2. So this is going to become -8. Notice I'm just letting it sort of float along. I'm not pulling it out in front of the integral symbol first, or the integration symbol first. Just going to have the -8 sort of float along. And we have -8 times, take that exponent, raise it by 1, so we have x to the -2 power. And then again, we're going to divide, because again, here we go, x to the n. When we integrate, we get x to the n plus 1, and we're dividing by n plus 1. So we're going to take that exponent, increase it by 1, and then also divide by that as well. Just want to make sure you get that completely set in. Plus c. So -8 divided by -2 is 4. X to the -2 plus c. And we're going to write this so we don't have a negative exponent, and have 4 over x squared plus c. This is the answer to our original problem. And I took up a lot of space here, plus my next example is not on the board, so I'll be right back. In our next example, we want to find the antiderivative of 1 over x squared times the square root of x. Now, again, we have a fraction bar, which means quotient, and we don't have any quotient rules in our basic integration formulas. We have the power rule. So we're going to have to write this. We also have, of course, a product going on here, and there's no product rule either, just the power rule. So we need to rewrite this so we can use that. That means we need to get rid of the fraction bar. So this is going to become the integral of x to the -2 times x to the -1/2 power. I'm going to write that radical as a power over root. The index here is 2, so that's x to the 1/2. And we move that out of the denominator, we get x to the -1/2 dx. Okay, so we got rid of the fraction bar, but we still have the product thing going on here, so we need to take those like bases and multiply them together and get the integral of x. When we multiply like bases, we add the exponents. So this is -2 plus -1/2, or what would that be? That'd be -2 over 1 minus 1/2. You need a common denominator, of course, so -4 minus 1 would be -5 over 2 dx. Now, I have the problem in a format that I can apply the power rule. And that means we're going to take this power, increase it by 1, divide by that same value, and so that becomes x to the -5 over 2 plus 2 over 2. That's, of course, 1 with the common denominator written out. Now, -5 over 2 plus 2 over 2, that's -3 over 2. So we're going to divide by -3 over 2 plus c. So we have x to the -3 over 2 divided by -3 over 2 plus c. And when you divide, of course, when we have this fraction in the denominator, we're dividing by a fraction that's the same as multiplying by the reciprocal. So we're going to take this bottom value of -3/2 and flip it up and make it a multiplication of -2/3 and get a final answer of -2/3 x to the -3/2 power plus c. Now, if you really want to get, do your simplification very thoroughly and get rid of all your negative exponents, this can be written as -2 over 3 times x to the 3 over 2 power plus c. And I'm sure that a lot of your teachers are going to be perfectly fine with having this fractional exponent. You could, however, write this as -2 over 3 times x to the first power times x to the 1/2 plus c. You see what I'm doing there? when you multiply like bases, you add the exponents. And when you add 1 and 1/2, you get 3 halves. I basically wrote, you can think of this as 3 halves being x to the 2 over 2 times x to the 1 over 2. And of course, 2 over 2 cancels out to be 1. And then we can put that radical notation back in because x to the 1/2 power is the square root of x. So you could write this as negative 2 over 3x times the square root of x plus c. So, it just depends on how far you need to go in your simplification process to make your teacher happy. And of course, you might have a right answer, but not have your answer in the format that's in the back of the book. So keep working on that simplification until you get something that is, in the back of your book so you can check your work. It's probably going to be in this format here with the x to the 3/2 power in the denominator. We have the, we want to find the antiderivative of 4x minus 3x squared with respect to x. And this rule here says that if we want to find the integral of two terms being added or subtracted together, we just find the integral or the antiderivative of each of those individual terms and apply the plus or minus function in the middle. So we're going to have the antiderivative of 4x is 4x. We're going to take that exponent and increase it by 1, so it's 2. And we're going to divide by 2, doing that power rule again, minus negative 3, or minus 3x. We're going to take that exponent, raise it by 1, that gives us 3, and divide by 3, and then apply that constant at the end. For each of the, you'd have a constant for each of those antiderivatives, but a constant plus a constant is just another constant, so we can write that plus c at the end just once. 4 divided by 2 is 2. X squared. 3 divided by 3 is 1, so we have minus x cubed plus c, and that's the end of that example. I got 2 more, or 3 more examples, so let's get those started. So, we want to find the antiderivative of x plus 4 over the square root of x dx. Well, we got that fraction bar, we have that quotient that we need to get out of there. We need to rewrite this again so we can apply the power rule. And we're also going to want to get rid of that radical symbol at the same time. That will allow us to get the problem in the format we need. So, we're going to, let's see, there's really nothing in the denominator that we can flip up. So what we're going to do is, we're going to see that we have 2 terms in the numerator, and we're going to pull those 2 terms apart and write 2 separate fractions for now. And that's going to be the integral of x over, now I'm going to write this square root of x, get it back into that rational exponent form. It is easier to work with. So we have a power and a root of 2, so it's going to be x to the 1/2 power plus 4 over x to the 1/2. And again, all with respect to x, we're doing this integration here. And now when you divide like bases, you subtract the exponents. So we have an exponent of 1 and we have an exponent of 1/2. So when we divide those like bases now in this format, 1 minus 1/2 is 1/2. So we're going to have the integral of x to the 1/2 plus 4, and I want to take this x to the 1/2 power out of the denominator, so we're going to have 4 times x to the negative 1/2 dx. And now I can use the summation rule, and of course I'm going to use the power rule on each of those 2 terms. So we get, let's see, we're going to use the power rule on x to the 1/2 power. So you're going to increase that exponent by 1, so 1/2 plus 1 is 3/2. So we have x to the 3/2 power divided by the 3 over 2 plus 4 times x to the, we're going to take this exponent now, working on that second term, raise it by about a value of 1, so negative 1/2 plus 1 is 1/2. And we're going to divide by that 1/2 plus our overall constant at the end. We're going to take each of these denominators and flip them up. So we have this 3/2 getting flipped up. The same thing as dividing by 3/2 is multiplying by 2 over 3. So we have 2 over 3 x to the 3/2 power plus, now if we take 1/2 and flip that up, 4 times 2 is equal to 8, x to the 1/2 power plus c, and that is our general antiderivative. Okay, so here we have x plus 1, the antiderivative. We want the antiderivative of x plus 1 times 2x plus 4 dx. Well, there is no product rule. We only have, the most powerful one we have at our disposal is the power rule. So we're going to want to distribute these binomials together and get it written in sort of like a polynomial form so we can use the power rule on each of those individual terms. So we have the integral of x times 2x is 2x squared. X times 4 is 4x, and 1 times 2x is 2x, so 4x and 2x make 6x. And 1 times 4 is equal to 4. All with respect, of course, again to the dx. So now we can do the integral, or find the antiderivative of each of those three terms. So we take this 2, so we have 2 times, raise that exponent by 1, so we have x to the third, and divide by 3, plus 6 times x, raise that exponent by 1, and divide by the same value, plus 4x, because the integral, the antiderivative of a constant, is equal to the constant, that same constant times x, plus that overall constant of c. And let's see, not much to clean up here. We have 2/3. X to the third plus 6 divided by 2 is 3. So plus 3x squared plus 4x plus c. Now, if you happen to be using, say, like a TID9 or a TI Inspire CAS version to check these problems, check your work by telling it to basically just do the integral for you, it will not be adding the plus c at the end of these equations or the end of these answers, so please be aware of that if you are attempting to check your work with those graphing calculators. I've got a few more examples. Here we go. Last two. Thank you for watching, by the way. I hope this is helpful. We want to find the antiderivative of 3 cosine x minus 2 sine x dx. If you're comfortable with this and everything's going really well, you might be able to just write the answer. I'm going to take the extra step to really rewrite this very specifically so that you see that we're coming up and matching these integration formulas, these basic integration formulas for the trig functions exactly before applying them. So we're going to write this as, let's see, we're going to use the sum and difference property to separate those integrals, and we're also going to move the constants out front. So this is equal to 3 times the integral of, we want to find the antiderivative, or the integral of cosine of x minus 2 times the integral of sine of x. Each one of these, whoops, forgot the dx. Dx minus 2 sine x dx. Got to remember what we're doing the integration with respect to. So the integral of the cosine of x is equal to sine x plus c. So this is going to be 3 times sine x. Because I have all these multiple terms, I'm going to leave the plus c at the end. Minus 2 times the integral of sine is negative cosine x. So negative 2 times negative cosine x plus c. Now, not much left to clean up. We just have negative 2 times negative 1. So we have 3 sine x plus 2 cosine x. And again, don't forget that plus c at the end so that we have basically an answer for the family of all of the antiderivatives. Now we have we want to find the antiderivative of sine of x over 1 minus sine squared x. And we've already discussed how there's no quotient rule in our list of general integration formulas. So if we can't get this to exactly match something we have over here, or that we can separate into separate terms, we're going to have a problem. We also don't have any of these formulas that say specifically 1 minus sine squared. Not that could be, that could be an issue. So what we're going to do is to attack this is to play around with the our trig identities, and see if we can't get this rewritten to a more friendly format. So 1 minus sine squared. Well, if you remember your first Pythagorean identity, sine squared plus cosine squared, or sine squared x plus cosine squared x equals 1. So if you subtract that equation by both sides by sine squared x, you get 1 minus sine squared x equals cosine squared x. So this becomes the integral of the sine of x over cosine squared x dx. Well, I still have a fraction in there. I still have a quotient, so that's no good. And I also don't have, this is the integral of cosine, sine, secant squared, secant. You know, there's nothing in here that we don't have a formula for doing the integral of cosine squared x. So what to do? Well, if I write this as the integral of sine of x over cosine x times 1 over cosine x dx. Well, now I can write sine over cosine, sine x over cosine x as tangent. So we have the integral of tangent x. 1 over cosine is secant x dx. And, the integral, see, I've gotten it rewritten to be exactly one of these formats here. The integral of secant x times tangent x dx is equal to secant x plus c. So this is equal to secant x plus c, and I've got that problem done, and that's the end of my last example. So, I'm Mr. True. Go do your homework.